Have you ever looked at the periodic table and wondered why some elements in the exact same family can act so differently? Well, today we're diving deep into Group 2, the alkaline earth metals. They might look straightforward, but their behavior follows a really neat hidden set of rules. And once you get them, you start to unlock the secrets of the whole periodic table. So let's jump in. Okay, so here's the puzzle for today. You take a piece of magnesium and drop it in water. You get a few bubbles, a slow fizz. But then you take barium, its cousin from just a few rows down, and do the same thing, and you get a seriously powerful reaction. They're supposed to be in the same chemical family, right? So what's going on? Turns out there's a family secret, and we're about to figure it out.
All right, first things first, let's meet the key players in this chemical story. So we're focusing on these four: magnesium, calcium, strontium, and barium. Each one's a little different, but as you'll see, they all follow the same fundamental family rules. Keep these guys in your head as we start connecting the dots.
First up, let's talk reactivity. This is where we find our first big clue, and trust me, it's a game changer. It explains pretty much everything about how they interact with simple stuff like water and the air around us.
Yeah, as we go down the group from magnesium all the way to barium, things just get more and more intense. And this is no accident. There's a beautiful reason for it. So what is actually going on inside these atoms that makes this happen?
It really all comes down to a simple two-step plan. For any of these metals to react, first, the atom has to ditch the 2 electrons in its outermost shell. Once those are gone, it becomes a stable, positively charged ion. That's the 2+ cation you see there. You can think of it like the atom is dropping some extra baggage to get to a more comfortable, stable state. And the easier it is to drop that baggage, the more reactive the element is going to be.
And this lays it out perfectly. For magnesium, up at the top of the group, those outer electrons are pretty close to the positive nucleus, so they're held onto really tightly. But when you get down to barium, there are way more layers of electrons in between. They act like a shield, blocking the pull from the nucleus. It's kind of like trying to hear a whisper from across a loud, crowded party. The signal just gets weaker. And that makes it way easier for barium to let go of its electrons and get a reaction going.
And you don't even have to go all the way down to barium to see this. Just look at the difference between magnesium and its next door neighbor, calcium. You put magnesium oxide in water, and it's a pretty tame affair. But calcium oxide, that reaction is so energetic it can literally bring the water to a boil. I mean, that's just a perfect real-world example of this trend in action.
So, we've nailed down how their reactivity changes. But that's just one part of the story. Now let's see what happens when these guys form compounds. Specifically, how well do those compounds dissolve in water? Because this is where things get a little weird.
See, when you look at their compounds, you find something that feels wrong at first. If you take their hydroxides, that's the metal combined with an oxygen and a hydrogen, they actually get more soluble as you go down the group. But then, if you look at their sulfates, the metal with sulfur and oxygen, the complete opposite happens. They get less soluble. How can one family have 2 trends that go in totally opposite directions? This table just lays out the mystery perfectly. With hydroxides, solubility goes up. This means calcium hydroxide is more soluble and makes a more alkaline solution than magnesium hydroxide. But with the sulfates, the trend flips. Magnesium sulfate, or Epsom salt, dissolves super easily. But barium sulfate is so insoluble that doctors actually have you drink it for certain x-rays. They know it won't dissolve in your body. It's just a fascinating contradiction, right?
Okay, we need one last clue. Let's look at how these compounds handle the heat. This is called thermal stability, and it's going to give us our final piece of the puzzle.
You've probably heard of limestone, which is just calcium carbonate. We know if you heat it up, it'll break down. But do all the carbonates in this family break down at the same temperature? No way. There's another super clear pattern here. And this chart just says it all. Check out how the stability climbs as you go down the group. Magnesium carbonate is the easiest to decompose, but by the time you get to barium carbonate, that tall bar at the end, it's way more stable. You have to crank the temperature way up to get that to break apart. And that is the last piece of evidence we need. Okay, so let's take a breath and recap. We've got reactivity that goes up, these 2 bizarre opposite trends in solubility, and stability against heat that also goes up. It sounds like a total mess, doesn't it? Well, it's not. It all ties back to a simple, really elegant explanation. And here it is, the aha moment. All these different behaviors we've seen, they are not random, not at all.
They're all the direct result of three basic things about the atoms themselves, and these things change in a perfectly predictable way as you move down the group. These are the three master keys to group 2. First, as you go down, the atoms get bigger. Simple enough. They're adding more layers of electrons, kind of like an onion. Second, those extra inner layers act as a shield, which makes it harder for the nucleus at the center to hold on to its outermost electrons. And the result of all that? The third key. The energy needed to pull off those outer electrons, what we call ionization energy, gets lower and lower. It's just easier. And that last one, that's the key to everything.
So it really all comes down to this one simple idea. The easier it is for an atom to lose its outer electrons, the more reactive it's going to be. Since that ionization energy goes down as you descend the group, the elements just naturally become more reactive. This one single concept explains everything we've seen today. It's the family secret we've been looking for.
So now that you've cracked the code for group 2, you can actually use this same logic to figure out other parts of the periodic table. For instance, think about the halogens over in group 17. Their whole deal is gaining an electron, not losing one. So, knowing what you know now, how do you think their reactivity changes as you go down that group? You've got the tools, give it some thought.